So here's a better method. It's a very classical method called binary search, and it's quite intuitive. So the idea with binary search is that, first of all, we put the whitelist array in sorted order. Now we're going to have to talk about how to do that, and that's the second part of this lecture. If it's in sorted order, then what we want to do is examine the middle key. If that one's the one we're looking for, then just return that index. We found it. If it's larger, then we know that our key must be in the lower half of the array, the ones with lower indices. And if that one in the middle is smaller than our key, then we have to look in the half with the larger indices. So for example, here's our list again, and we're looking for Oscar. We check in the middle. Is that key there Eve? Is that the key we're looking for? And the answer is no. Our key's bigger, so we can eliminate the first half of the array and just look in the second half. Then we look in the middle of that one. In this case, it's Peggy. Our key's smaller. Now we can eliminate the top half of the array and concentrate on the lower half of that part of the array. And again, Oscar, it's not Mallory, so we know it has to be bigger. And eventually we get down to where we find our key, or we get to an array of size 1 that's not equal, and we know that our key's not there. One of the two must be true. So in this case, we found a match, we return 10. That's binary search. So it takes a little bit of arithmetic. We'll use a math-like notation. If we say A of square bracket, low comma high, where low and high are indices in the array, and then a regular parenthesis, that means that we are considering A of low plus 1, all the way up to high minus 1, but not high itself. It's an open interval in math, and the same thing works for an array in Java. And so if we're looking in this part of our array, where we include low and not high, high is bigger than low, or equal to it. Then if we want to look in the middle, the way we get the middle is subtract our two indices, divide by 2, and then add that to low. So the number of elements is high minus low, you divide that by 2, that's half the size of the array, and you add that to low, that's our middle. And then once we've compared our key against mid, we don't have to consider that one anymore. So we just include it as with the open parenthesis to exclude that in the lower half of the array. And then the upper half of the array, we do mid plus 1, and then again we use high but exclude A of high. And this is just a detail that helps make the arithmetic easier to check when we implement the recursive routine that's going to do this. You need to study it a little bit. It's easy to get this wrong, but it's worth it to take a quick look at this. Okay, with that in mind, let's look at the Java code for implementing this search. So that's the method that we're supposed to implement, taking our key and the array as arguments. And we're going to call a recursive routine that also includes the indices within the array that we're concerned with. Low and high, as on the previous slide. So that's all set up. The array goes from 0 to a.length minus 1. So with our open interval notation, if we call the recursive routine from 0 to a.length, we're doing exactly what we want, search the entire array. And then recursively, we check that our high is bigger than our low. If it's equal, then there's nothing in the array, or even if it's less, there's nothing in the array. So that's our termination condition. That's an unsuccessful search. We never found our key. Then we compute the index of the middle element, just as on the previous slide. And we compare that element against our key, and just that's result is minus 1 if our key is less, 0 if it's equal, and 1 if it's greater. And then we just test that to see whether we're in the left part of the array, in the right part of the array, or the part of the array with bigger indices, or if it's not greater or less, then it's equal to 0, and then we return successfully with the index that contains the key. So that's a recursive method that solves this problem. Again, it's easy to make mistakes in this. It's worth a study. It's worth some study, but it's basically a pretty simple program once you make sure that you have some discipline in making sure that you test for the case when it's empty or it's got just one key, as we have. Okay, so here's what it looks like, say, with the recursion trace. So in our example, searching for Oscar, we're searching for from 0 to 15. So to do that, then we compute 7. Oscar's bigger than Eve, so then we go to the higher indices from 8 to 15. And now the middle's 11, Oscar's less than Peggy, so now we go in the part with the lower indices, that's 8 through 10. Now the middle's 9, Mallory, Oscar's bigger than Mallory, so we go to the part with higher indices, 10 and 11. 10 and 11 is just an array of size 1, and that's where Oscar is, so we return that index. And then we go back up the recursive tree, returning that value all the way up to the main, return 10, and that's a successful search. All right, what about let's do a mathematical model to study this method. For simplicity, we'll do an exact analysis when the number of keys is a power of 2 minus 1, and you'll see in a bit why it works that way. So if big N equals 2 to the little n minus 1, then little n is about log base 2 of n. It's actually equal to log base 2 of n plus 1. But let's look at what happens in this case. So if you subtract 1 and then divide by 2, you're always going to get, for the first call, it's always 2 to the little n minus 1. But if you subtract 1 and divide by 2, for the second call, it's always going to be 2 to the n minus 1 minus 1. And again, subtract 1, divide by 2, the size for the next call is 2 to the little n minus 2 minus 1. You keep going that way, eventually we get down to always, for the nth call, the subarray size is going to be exactly 1. So every search miss is going to be a top to bottom path in this tree, and the total number of compares, so for every call we do one compare against our key against the middle key in the current array. The total number of compares is going to be little n, which is about equal to log of big N. That's an indication of how binary search gains its efficiency. That is a proof that binary search uses about log n compares for a search miss. And with a little more work, you can show that same is true for a search hit, and it doesn't matter if it's a power of 2, you still get these same results. So these are kind of interesting exercises in discrete math, but you can see that the running time is going to be proportional to log n for whatever n is. And you can learn more about this maybe in a course on algorithms. But understanding it in terms of when n is a power of 2 minus 1 is fine for our purposes. So our model is that the cost of a search is going to be log base 2 of n, about log base 2 of n. That's the point of this mathematical analysis. And again, we want to test this empirically. And Alice has already signed up for the course on algorithms. Let's do our empirical test for the scenario that we considered for sequential search. And again, we'll do the same story. And now we'll test binary search, not sequential search. So in this case, for 100,000, it takes just 1 second. For 200,000, 3 seconds. For 400,000, 6 seconds. And now our ratio is a lot closer to 2 than 4, and we can go up to 1.6 million, and it's only taken 30 seconds. Remember, for sequential search, it was taking hours. So for 10 million, you can do it in a few minutes, and the ratio is about 2, and we're at about 50,000 transactions per second in holding. So that validates the hypothesis that each of the n searches takes time proportional to n log n. That's something that will scale. And binary search is certainly a much more effective method for solving this problem than sequential search. But the question is, how do we get the list into sorted order at the beginning? That's the thing that we're going to have to consider next.